First of all, let's look at this function f of x, which is equal to x squared plus x minus 12, and I want to ask about the domain of this function. The domain, when we're talking about x values, one way we can describe domain is what x values are we allowed to plug into the function that are not going to cause anything to go wrong. And in this particular function, there are no restrictions on x values. We can plug in any value from negative infinity up to positive infinity. In this function, by contrast, which is g of x is equal to 2 divided by x plus 5, we do have some domain restrictions. If you'll notice, this denominator does not want to equal 0. So x plus 5 is not allowed to equal 0. If we subtract 5 from both sides of this little does not equal equation, we find that x is not allowed to equal negative 5. This is one way we could present, and my pen is not working anymore. This is one way we could present our final answer regarding the domain. Another way, using interval notation, is to make a list of x values that we are allowed to use. And those x values go from negative infinity all the way up to negative 5. Exclude negative 5 with the parenthesis or open bracket, or, that's the union symbol, we can choose x values that come from the interval starting at negative 5, but excluding it all the way up to positive infinity. And this is probably the better way. It's a longer way, but it's a more formal way to list the domain because we're listing x values that we are allowed to use. Let's look at one other function. We'll call this one h of x, and it's equal to the square root of x plus 2. When we're taking the square root of a number, we can definitely take the square root of a positive value. We can take the square root of 0. Note, the square root of 0 equals 0 because 0 squared is equal to 0. But at the moment, I don't want to take the square root of negative numbers. So I'm going to take this quantity under here, which is called a radicand, R-A-D-I-C-A-N-D, and I'm going to say that I want to make sure that the radicand is greater than or equal to 0. So we're talking about x values that we can use right here. And if we solve this statement for x, we find that x values are allowed to be, or we want them to be, greater than or equal to negative 2. This is one way we could state the domain for the function h. Using interval notation, well, let's actually look at a number line first. Sometimes I like to look at my values on a number line. Here's 0, here's negative 2. The x values that are greater than or equal to negative 2 are over here, and they go all the way up to positive infinity. So in interval notation, I'm going to include the value of negative 2 because we have a greater than or equal to symbol. So that tells me to use this square bracket, and we're coming all the way up to positive infinity. And positive infinity takes a parenthesis because we can't ever really get up there and get a handle on it. All right, so that's an initial conversation about domain of functions. And that's going to play a key role in our conversation about composite functions. I'm multitasking poorly over here. I don't know if you can hear in the background. I'm clicking and things are not happening. All right, so let's look now at the algebra of functions involves adding, subtracting, multiplying, and dividing functions. So let's give ourselves a couple of functions to work with. We can take our two functions, f and g, and add them together. Sometimes you'll see it written like that. Sometimes it will be written like this. That statement is equivalent to writing f of x plus g of x and keeping them separated. I kind of like writing it that way because I can see pretty clearly that f of x is equal to x minus 6. I'm going to bring my addition symbol down here so those match up, and then g of x is 5x squared. I'm going to put that in parentheses because when I do substitution I like to use parentheses. There isn't any combining of like terms that we can do here. The only thing I'm going to do is rearrange my terms a little bit, and I end up with 5x squared plus x minus 6, and that is the combination or the addition of those two functions. Let's try subtraction. Let's take f minus g of x, that's the same thing as f of x minus g of x, and we have x minus 6 subtracting 5x squared. You could say that we need to distribute this minus sign into that set of parentheses, so getting rid of our grouping symbols, we could write this as x minus 6 minus 5x squared, and then reorder them as negative 5x squared. The x was positive, the 6 was negative, and we could write this as our final answer. Now I'm going to try to make a good habit of writing some little notes in the margin. DIST stands for distribute, so that's what we did in taking this minus sign and bringing it into or distributing it into these parentheses, and then I suppose we could write reorder or rearrange. Use whatever language in your own notes works best for you. Alright, let's talk multiplication. F and then a little solid colored dot. It's not an open circle, it's a closed dot. F times g. So we've got f of x, if you want to put a dot there also, times g of x. And let's fill in those blanks. Let's make our substitution. F of x is x minus 6. G of x is 5x squared. And we have to multiply. Now, this is a little unusual. Remember that, for example, 2 times 3 is the same thing as 3 times 2. That's the commutative property of multiplication. So I can apply that idea here and swap these two sets of parentheses and put the 5x squared first and the x minus 6 second. And you might like the idea of doing that because it's a little bit more comfortable for most of us to do our distribution from the left. So the 5x squared is going to multiply in and impact both sets of those parentheses. But realize that we could have distributed in from the right, and we'd have the same result multiplying the 5x squared in from the right-hand side. Let's get rid of those arrows so those are not confusing later. Let's do the distribution. So we have 5x squared times x makes 5x to the third. 5x squared times negative 6 makes negative 30x squared. And that is the result of our multiplication. Not a very good box written there, but you get the picture. The division process, dividing f by g of x, is not going to be too exciting because of what our functions are, but just to get a feel for the process, I'm going to keep working my way to the right here. F divided by g, so I've got x minus 6. I'm dividing it by 5x squared, and I'm going to stop there because there isn't anything I can do. I cannot cancel out one of these x's. I cannot do that. Alright, I can't do that because this is a term and this is a term, and the only thing that we're allowed to cancel out are common factors. But those are not factors, those are terms. So we're going to leave them be for now, and in a later video we'll see some reducing that does involve canceling stuff out from the denominator where we are able to divide into both terms. But that's not happening right now. Okay, So that is the algebra of functions. And now we're going to finally get into the actual composite of functions. And let's mix it up and use a couple of new functions. Let's work with functions f of x equaling 7x plus 1, and g of x this time will equal 2x squared minus 9. And what I want to do is introduce the notation to you. That's a little open circle between the f and the g this time. And when we read this, we say f of g. I don't like that. I don't like either of those parentheses. F of g of x is how we would read this. Another way to write this that makes it look even more like a composite function, where we're putting one function into another, is to write the g function as though it is actually an input value into function f. And so I prefer to think of it that way. And since I'm the one with the pen, that's how we're going to do it. Let's see. All right, so let me back up just a moment. Let's put a little note here. If I wanted to evaluate f of 2, we know that we would take the 2 and plug it, jump the gun there, plug it into our function f, and so the x has been replaced by a 2 because we replaced this x with a 2. And then we do some arithmetic and we get an answer of 15. Great. I could replace my x value with something random like an m, and we would get 7 times m plus 1, and there's nothing we can do with that, so we'd get a final answer of 7m plus 1. Could I replace my x value in my original f function with another function? I sure can. And so let's do that. 7 times g of x plus 1. You'll see I'm using my parentheses in the same way. See the parentheses right here after the 7? Yep, they're all there. See the parentheses after my input value? Yep, Whew, they're all there. Okay, and then the 2 came in, and the m came in, and the g of x came in, and there they are inside my parentheses. Wow, that's a big mess. All right, let's get rid of all that. Now, I'm going to make another substitution. I'm going to replace g of x with what g of x actually is. So let's take g of x and bring it snaking down into here, and let's replace this. Connect that. Good. Let's replace g of x with 2x squared plus 9. Make sure to close the parentheses. Don't forget the plus 1 at the end. So we can call this substitution, maybe. I mean, it definitely is substitution. But if you want to title it like that. So this substitution is what I'm doing in order to go from this line down to this line. And that is a sort of how I structure my notation. So I'll do that pretty consistently. The next thing I want to do is distribute. That turned out to be red. That's okay. Let's switch to black again and do our distribution. The 7 times 2x squared has to happen. 7 times the positive 9. Let's see, the results of that are 14x squared. 7 times 9 is a positive 63. The plus 1, you see them lining up there. I'm keeping my organized work, even though I've got bad handwriting. Things are lining up there. And the last thing we'll do is combine like terms. CLT for combine like terms. 14x squared plus 64. And that is how we work with composite functions. Now that we have f of g of x, we could evaluate f of g of 2, and we could plug an actual number in for our x value, and we could work through the arithmetic of doing 14 times 2 squared plus 64. I don't have any interest in doing that arithmetic, but you could do it if you wanted to. Because of our original functions, f of x and g of x, that are near the top of the screen here, this function I'm circling does not have any restrictions on it. There's no danger of division by 0. There's no danger of square rooting a negative number. In the function g of x, no square roots, no division, potential division by 0. So we don't have any domain restrictions there. So at least initially in talking about domain restrictions in composite functions, no worries on that one. Let's, however, look at one other example of a composite function where we should be paying attention to domain restrictions. Let's look at, let's separate those, come up here a little bit, and let me give you some new functions, f and g. These names of these functions are totally arbitrary, okay? We could call them whatever we want, really. Let's do that. Let's get rid of the f, let's get rid of the g, let's be more creative. Oh, I don't want to be too creative. You could call them star and heart if you wanted to. It's kind of a sad looking heart, but some hearts are more perky than others, I suppose. Let's try it. It's a little weird, but just to drive home the fact that we can call the functions whatever we want, doesn't always have to be f of x. And let's build this composite function. Well, actually, let's first make a little note about domain restrictions on this function. We know that we don't want the denominator x plus 5 to equal 0, and we don't want this denominator of x to equal 0. So I've got a does not equal sign on both of those, and only on this first one for the star function do we have to subtract 5 from both sides. So we'll take note that x is not allowed to equal negative 5 there, x is not allowed to equal 0 there, and then let's get into building the composite function. Let's build star of heart of x. So we're taking the heart function, plugging it into the star function, so we're going to end up with heart of x over heart of x plus 5. I've replaced my x's in my star function with heart of x. And so there they are, heart of x and heart of x. All right, now let's replace the heart of x's with what they are. Heart of x is equal to 6 over x. This one is 6 over x. The plus 5 is still there. Now, the fact that heart of x is the, how should we get there? Let's go this way, is the inner function. This means already that x is not allowed to equal 0. Okay, this is very important. We're looking at our domain of our inner function, right? The one that's inside these parentheses over here. The first thing that's going to happen when we plug in an x value is that x value is going to go in here. And what happens to that x value first? This heart function. And if we look up here a little bit at the heart function, we see that it has this restriction that says x is not allowed to equal 0. So already that's why I have very enthusiastically circled it in red, is because we want to make sure that we don't use that x value of 0. I was trying to get rid of some other stuff. I'm deleting the wrong things now. We're coming over here. X is not allowed to equal 0. There's the enthusiastic circling again. Very good. Thank you. And let's get rid of that stuff and that stuff. Okay. Now I'm here. I've built my composite function. I've plugged in or replaced or substituted in for heart of x. Let's clean this thing up. I'm going to work my way from left to right across the page. I'm going to leave my numerator of 6 over x there. In my denominator, I have this 6 over x, and I'm going to write this 5 as a 5 over 1 so that I can multiply it by x over x in order to achieve a common denominator. Let me keep going over here. 6 over x all divided by 6 over x plus 5x over x. That's not an x. That's an x. All right, now down here, I have a common denominator, so I can add those two fractions together. Let me move over here in black, please. The 6 over x in the big numerator is going to stay as it is. In our denominator, we'll add those together, the 6 and the 5x, and those are now all over their common denominator of x. And because I have a fraction divided by a fraction, I can keep, change, flip, or division is the same thing as multiplying by the reciprocal. So I keep my numerator, I change division to multiplication, I flip my denominator, 6 plus 5x, and we will now be able to cancel out these x's and write our final answer as 6 over 6 plus 5x. Not my best plus sign ever, but nobody's perfect. It's just a little guy. Okay, this is, I'm going to put a box around this, a little wavy box. That's our final answer. That's our composite function. But I'd also like to make a note, because it's not that I'd like to make a note, I have to make a note. This denominator of our composite function, 6 plus 5x, is not allowed to equal 0 either. So we have to, oops, hello. Excuse me, we have to sort this out. So I'm going to subtract 6 from both sides. 5x is not allowed to equal negative 6. Divide both sides by 5. X is not allowed to equal negative 6/5. Enthusiastic circling. And we now have two values that need to be left out of our domain. So let's make a quick statement about our domain. Oh boy. We'll stay in red. Our domain says that x is not allowed to equal 0. That's not a 0. Comma, x is not allowed to equal negative 6/5. Let's put it on a number line. Here's 0. Here's negative 6/5. We would leave an open circle here and an open circle here, and we could shade everywhere to the left of that one, and everywhere in between these, and everywhere to the right of 0. And if we translate that down into interval notation, the shading starts from left to right, starts down at negative infinity, comes all the way up to negative 6/5, excludes it, or the union symbol, or we can choose x values from negative 6/5 up to 0, or we can choose x values starting at 0 and going up to positive infinity. So this domain is a very important component of our final answer. And if you were taking a test or a quiz, the domain itself could be a question, but I don't think you'd ever see just the composite function alone, because the domain is such an important component of that as a final answer. All right, hopefully that is helpful in your learning about composite functions and domain restrictions. All right, so there's your composite function, there's your domain restriction, and you're off.